So when we're looking at this graph, we're going to pay a little bit of close attention to our local extrema. This particular graph has a local minimum at -5 and another local minimum at -2 or +2. We have a local maximum at -1 and another local maximum at around 7. So we're going to pay attention to the value, what kind of value we have at each one of these points, the value of the first derivative and the value of the second derivative. And we're going to pay close attention to whether or not these values are positive or negative. So our very first local minimum we had was x equals -5. For x equals -5, f of -5 is something that is negative. F prime of -5, if we consider its tangent line, would be equal to 0. And f double prime at -5 would be a positive value since the graph is going to be concave up in that area of -5. For the other local minimum at x equals 2, f of -2 would be 0. F prime of 2 would be something that does not exist since we have a corner located at x equals 2. And since we don't really have an equation that we could really solve for and experiment what's going to happen, we're just going to assume for right now that the second derivative also does not exist for this corner. In terms of the maximums, for our first local maximum at x equals -1, this would have a positive value for the actual point. Its first derivative, if we consider the tangent line, would be 0. And the second derivative at -1, since we're dealing with a concave down function, would be something that's negative. And then at x equals 7, we have again a positive value of the point. Our tangent line would indicate that we're going to have a 0 first derivative. And once again, we are concave down, so we're going to have a negative second derivative. So if we take a look at the second derivative specifically as it relates to local mins and maxes, as long as we have a first derivative that is 0, we can take a look at the second derivative to determine if it's a min or a max. A local max is going to have a second derivative that is negative. And that's because we're working with a concave down portion of the graph. So for the concave down portion, where we have a horizontal tangent line, we're going to be dealing with a maximum. For local minimums, if we have a positive second derivative, we have a concave up section of the graph. And again, if we have that horizontal tangent line, we're going to be looking at a local minimum. If you notice, this rule doesn't quite apply for when we have a do not exist situation for our derivatives. So this is really focusing on when our first derivative is 0, when we have that horizontal tangent line. We can investigate our second derivative to determine what type of concavity we have in that area of the graph, and then make our assumption about local mins and maxes from there. This is our second derivative test. So the second derivative test will find you the local extrema. So we're going to start off with f prime and set it equal to 0, and we are also going to check the does not exist values, basically finding your critical points. Then what we're going to do is actually take those actual critical points we find and plug them into the second derivative. And then we'll report out what we find. If the second derivative at the critical value ends up being positive, we have a concave up section of the graph, and we're dealing with a local minimum. If the second derivative is negative, then we have a concave down portion, and we're working with a local maximum. If, however, we notice that f prime equals to 0 or does not exist, then we're dealing with a situation where our second derivative is not useful for us, maybe because there's a corner or a cusp or some sort of discontinuity. So we're going to have to try another strategy, like maybe going back to that first derivative test to help us analyze where the local extrema may happen. So here's our example. We're going to look at both the first derivative test and the second derivative test to solve this particular problem. We have our function f of x, and we're trying to determine where its relative minimum is going to be located. Whether you use the first derivative test or second derivative test, you're both going to start them off the same way by finding f prime and setting that equal to 0 and does not exist to find your critical values. So our two critical values end up being x equals 2 and x equals -1. So for your second derivative test, our next step is to actually find the second derivative. You can also factor this if you feel like it's going to help you out. Well, what we're going to do is we're going to take those critical values of 2 and -1 and just plug them straight into the second derivative itself. What we're looking at when we investigate our second derivative and plugging those critical values into that is to determine whether or not our second derivative is a positive value or a negative value, and thus trying to look at the graph and determine, are we dealing with a concave up section or concave down section. So at f double prime of 2, we have 12 times 2 minus 6. That will be a value that is positive. So that would be a section that would be concave up. For f double prime of -1, we're going to end up with a negative value, and that would be a section of the graph that is concave down. So what we know is we have a concave up section at x equals 2, so we have a local minimum there. So we can say something like at x equals 2, f prime of 2 is equal to 0. We found that up in the top part, finding our critical values. And f double prime at 2 is greater than 0. X equals 2 is a local minimum. We have a horizontal tangent line and the graph's concave up, so therefore we have a local minimum. All right. At x equals -1, f prime of -1 is 0, and f double prime at -1 is negative. X equals -1 is a local maximum. So we look back up at our answer choices. We're looking for a relative minimum, and our relative minimum that we found was at x equals 2. Now, if we compare our second derivative work with what we'd have to do with our first derivative, we still start off the first derivative test the same way, where we still look for our critical values of 2 and -1. But in the first derivative test, we'd have to do a little bit more of the plugging in. And here's what I mean. So for your first derivative test, we put those critical values on a number line, and we have to test all the intervals around those critical values. So in this case, I chose something like -20 all the way on the left, a 0 in between the two critical values, and then a +20 all the way on the right. And I had to test 3 different values and determine if they were positive or negative. That indicated whether or not the graph of f was increasing or decreasing. And then we can look back at our various intervals and the increasing, decreasing to determine where our local max and local mins were going to be. So both of these tests are effective in finding local mins and maxes. You are going to start off the same way by finding the exact same critical values out of your first derivative. But for your first derivative test, you will stay with the first derivative and just plug in other values into that first derivative test. For your second derivative test, you will find the second derivative and take the critical values as the numbers you're going to plug into your second derivative.